So it's a great pleasure to have today's colloquium for Francois Labourie, who's going to talk about character varieties and so on.
Okay, thanks for the invitation. I think the first and last time I was here was a long time ago. It was just after your honeymoon, for a car issue.
Oh, yeah, wow.
Yeah, that's only a thing I remember.
That was 96.
Yes, 96, yeah. So, so I guess the point that I was invited by Bob Zimmer at the time, so I guess Simeon wants to be the next president. So that's what I guess from the invitation. So anyway, I want to talk about character varieties and Poisson brackets. And this is a joint work with Martin Bridgeman. So I'm going to spend a lot of time with the basic elementary things. And the first thing I want to talk about is what is an algebra? Okay, so an algebra is just a vector space, a real vector space in my context, equipped with a product. And this product, the only thing that we require about this product is that it's a bilinear map. So that's not a lot of requirements, but of course, there are lots of different types of algebras, and I'm going to be interested into associative commutative algebras. So I'm going to define them. I'm going to define also Lie algebras, and finally Poisson algebra. Okay, so let's explain a little bit what are a commutative associative algebra. So the only thing that you should remember that the product is usually not denoted with a dot. And this product is both commutative and associative. Can you believe it? So, so there are several examples of that. And one of the most useful example, of course, is the case of the polynomial algebras. You just take polynomials into finitely many variables. But of course, you can take polynomial algebra over a set where the variables are now into a set, not just into a finite set. Another case of commutative associative algebra is, of course, a space of function on a given manifold. Right, so far, so good. So Lie algebras. So again, the most important thing about Lie algebra is that the product is denoted by a bracket. So then you have two different properties, which are some sort of the mirror of the commutative associative one, which is the antisymmetry, and the Jacobi identity. And so there is a band-aid. I don't know what's going to be. Oh, right. So some example that you may have heard about, which is the case of the n times n matrices, and then you have the product. The Lie bracket is given exactly by this formula with the multiplication of matrices. Of course, all this has been very elementary. So now I'm going to give you another example, which is actually due to Bill Goldman, which is an infinite dimensional Lie algebra, and which is a topological object. So you start with a closed, let's say, a closed surface, and first you have this notion of for an important thing about surfaces is you can draw curves on them. So that's a different type of curves, and you have a notion which in French we call free homotopy, and apparently on this continent you call it homotopy. Is that correct?
We call free homotopy.
You call it free homotopy? Oh, but just Canada. Okay, so yeah, I know this is a free country, so it should be free homotopy. So right, so you just the notion is just that you can deform them. So obviously the blue curve and the green curve and the red curve, they're all freely homotopic, while this one is not homotopic to this one. Yeah, it's not. You sure? It's not. Yeah. And so let's use some notation, and we denote by C bar the free homotopy class of a curve C. So I'm not going to denote it by a bracket because I'm going to take brackets of this stuff and it's going to be too messy. Right. So what is a Goldman algebra? So you start with the vector space, which is just the vector space generated by this free homotopy classes of curves. It's just a set of those finite sum of these curves. And we are going to define a product of this vector space. So like we just to define it on generators. So what do I do here? I pick two curves I'm going to give you an example in the next slide. And I take the sum over so there is a sign. So I take the sum for the guys which are in. Sorry. So again. So I pick representative of my classes, C1 and C2. So I'll assume these two curves, they intersect transversally in only finitely many points. And then I take the sum over the intersections of epsilon x. So this is a sign which is either +1 or -1. So which correspond to, so your surface has to be oriented. So your curves are oriented, so you can define whether they intersect positively or negatively. And this is the two cases that appear here. So this, you have a sign which depends on that. And then what you can do is that at the intersection point, you can compose. So now your curve as C1 passes through X, and your curve C2 passes through X. So you can just compose the two curves at the point X. So in other words, if C1 is followed by C2, so look at this little picture here. Okay. No, sorry, here. Right. So if in my convention C1 is a blue thing and C2 is a green thing, so what you do is you first do C1, and then you compose with the green thing. So that's amount to sort of changing the curve near the point and doing, so you first go along C1, and then you go along C2, right? So that's a very simple product that you can define, even though it's only defined on nice representative so far. So, right, so let's see an example. What is the product? What is the product of these two curves? The green curve and the red curve. Right, so you have two intersection points. So it's going to be the sum of two curves. So you perform your first little transformation over this point here. And here the intersection is +1, if I'm correct. And then you replace your curve by your sequence of green and blue by this blue curve. So that's going to be this curve which is drawn on the spot on the top here. And you can also perform the same thing for the lower example, the lower point. Or actually, yeah, for the lower point, and I can this new curve. So this way I obtain a product defined on curves. So far so good, except that well, there is an exercise which is kind of fun, which is to understand that actually, if you, which is easy to do, if you take to show that this bracket is antisymmetric, right? That if you exchange the role of C1 and C2, you're going to change the point is that of course C1 followed by C2 is freely homotopic to C2 followed by C1. And this shows you that the Goldman bracket is antisymmetric. And what is more important is that this bracket does not depend on the representative C1 and C2. It's not very difficult to show, right? And what is a little more surprising is that this bracket is actually a Lie bracket. It satisfies the Jacobi identity. So, of course, I'm doing some reverse engineering here, and Goldman obtained this bracket by considering a resultant character varieties on the surface. So I'm going to explain that a little more. So is that clear? So that's an example of a Lie algebra. And I guess most of you have never heard of it before. It's a pretty cool algebra, and it has also some application to three-dimensional invariant, because that's not good. Okay, so what is a Poisson algebra? So Poisson algebra, now you put together the two structures. So you have a commutative associative product, which is given by this dot here. And you have a Lie bracket, and the convention for this Lie bracket is denoted by, how do you call this symbol? Braces. Braces. And so on one hand, this braces satisfies the Jacobi identity. And of course, these two have to be coherent. And the coherence is given by this Leibniz rule, which is like you think of the bracket as a derivation. And if you derive the bracket AB by C, it's just A times the derivation of B by C plus B times the derivation of C by A. So, and then there's something below, which I don't know what it is. Oh, a simple example. So here's a very simple example. And you start with a polynomial algebra in two variables, x and y. So it is, of course, a commutative associative thing. And now you want to define the bracket of two polynomials, two such polynomials. So it's enough to define the bracket for the two generators and then expand it using the Leibniz rule. So it's enough to define the bracket so that the bracket of the two variables x and y is equal to 1. And this allows, by the application of the Leibniz rule, to define what is the bracket of two polynomials. Okay, so that's an important example for many reasons, and one of the reasons that its product is combinatorially defined. I mean, you can compute the brackets of two polynomials is just a function of the coefficients. So of course. Right. Okay, so why Poisson algebra? So
throw the paper in the trash can. It wasn't big. It was very.
it's not, don't worry. Don't worry. Okay. I saw someone was complaining about Poisson algebra. So why Poisson algebra? So one of the answers I just discovered was a rhetorical question, of course, but then I discovered the answer while entering your building. Have you seen that? So it's so I just saw the list of this mathematician, and there is Hamilton. So why Poisson algebras are important? Because Hamilton is related to Poisson algebra in this building, right? So it's really good, right? I should say that Poisson is on the Eiffel Tower, so it's way cooler. Okay. So what is important is the Hamilton's formulation of classical mechanics. So let's wave my hands a little bit. So if you want to study mechanics, or then you start with a manifold and you have a particle, a point moving in this manifold, and you consider this space is usually called the configuration space. And the point of Hamilton was to say that it's quite important to consider the phase space, which is a cotangent of the boundary, rather than the tangent to the boundary. And this cotangent is called the phase space, and we consider the positions and the momentum. And the way to formulate Hamilton's equation is to show that actually this specific commutative algebra has a Poisson value. And usually say that cotangent has a Poisson structure. That's right. So how is Hamilton formulation exactly given? So you have a system which is described by a Hamiltonian, which is a function of the cotangent space. And what you want to do is you given a particle, and you want to know where it is, or the value of the function of the position of the particle at time t. So in other words, you start with a function, and in this context, you usually call functions observable, and you consider the family of function f sub t of x, t is the time, which is just the value of f for the particle, which is at time 0 at x, and at f of, well, it's written here, f of xt And xt is just the trajectory of the particle, which is at time 0 is at x. And the point of Hamilton is that these functions, this familiar function, depending on time, satisfies a very nice, simple evolution equation, which is given by exactly by the Poisson bracket. So, so here, just a little note for me, just to remind me that to tell you that it's quite important that when you know that this bracket is defined in a combinatorial way, because then you kind of turn your problem into a more combinatorial problem. So, for example, there is a case of cluster algebras or integrable systems or what. So I just said that the cotangent bundle of a manifold has a Poisson structure. There's lots of other objects which have Poisson structure. And from my point of view, is the case of character varieties, and I'm going to link that with Goldman algebra before. So you start with a compact surface S, and out of this compact surface, you can produce a group, which is a fundamental group, called the fundamental groups, which if you don't know what it is, I'm not going to explain you that right now, but okay.
Everybody knows.
Okay, so that's hopefully. And so then when I have that, then I can consider this object which are character varieties, which are essential. Well, I'm oversimplifying it, but please don't protest too much. So this is the space of homomorphism of your fundamental group into some linear group, and you divide it by the linear group itself, meaning that you take that two representations are the same whenever they are conjugate. So a way to see that for people with more differential geometric point of view is to consider the space of flat connection up to gauge equivalence. And the point that this has a complex structure. This has the Poisson structure. On one of the cases that you definitely know about is that when you take n is equal to 1, so you're talking about the representation of pi1 of s into R. And the character variety is nothing else than the H1, the first homology group on the surface. And we know that this has a symplectic structure and hence a Poisson structure. Okay. Right. Now, when you have something with a Poisson structure, what you like is to have a natural subset of observable, natural subset of functions. So here, this actually is an algebraic manifold, and there is some, you may consider the space of algebraic functions, and they are essentially, in most of the case, generated by what are called Wilson loops, and that's what we call characters. So, so how do you define a Wilson loop? So a Wilson loop is associated to a closed curve on your surface. And what you do is just this closed curve, you consider this free homotopy class. So this free homotopy class corresponds exactly to a conjugacy class in the fundamental group. And what you now want to do is that given a representation of O here, the Wilson loop associated to the curve C is just a trace of rho of gamma. And the fact that everything is invariant under conjugate, I mean, this is the representation may well be defined just up to representation, up to conjugation, but then the trace takes care of that. So that's a natural class of functions on a character varieties. And essentially, there are not really any other functions for general character varieties. Okay, so now the question is, what is a bracket of two Wilson loops? So the answer is given exactly by the result of Goldman. If you take the Poisson bracket of these two Wilson loops, it's exactly the same thing as the Wilson loop associated to the Goldman bracket of the two functions. So the very topological thing I defined before is related to the Poisson structure of character varieties. Well, of course, here I define a Wilson loops for formal sum by extending linearly. Okay, so that's a explanation of maybe a normal reason. Okay, so now now I'm going to move to the last part of my talk, which is a less more particular, which is I'm going to talk about Anosov representation. So so Anosov representation are a very specific case of a representation of, let's say, in our case, a surface group into SLE, which satisfy some kind of dynamical properties. So, right. So, take your surface and imagine your surface is a quotient of the hyperbolic plane, right? So, what is a projective Anosov representation? It's just it is the point that you need to know here is that if anytime you have a pair of you have a geodesics in H2, you obtain a rank 1 projector the endomorphism. Okay, so maybe I can try to write here. So I have S. So let's draw this hyperbolic plane, and the geodesic is just a correspond to a pair of points that joining a point X to a point X. So what is another representation? It associates to every geodesic a projector, depending on the representation, and it's a rank 1 projector. It's a projector on a line parallel to a rank 1. Right. So of course, this has to have some relation with the representation. So far, there is no relation. So the relation is that just if you take the image of your geodesic by your surface group gamma, then the new projector is just the image of the projector by this endomorphism. Right. So that's one of the conditions. So there is a condition I will not talk about, and which is why we're talking about Anosov thing, which is that this object, should correspond to a splitting of some bundle of your unit tangents bundle of the surface and that this bundle should split us in some Anosov. So, but for this talk, we just use the fact to present the result that to every geodesic you have a rank 1 projector. So what is written here? Right. Okay, so now the consequence of the hidden dynamical stuff I didn't say about is that the space of Anosov representation ends up being an open set in the character variety. Okay. So my purpose now is to explain that associated to Anosov representation, associated to this specific open set, you have many more observable than you can do just for classical character varieties. And moreover, what we did with Martin Bridgeman is to compute the Lie bracket of this observable. Okay.
So you saying that this was not entirely the complete definition?
It's not entirely the complete definition, right? So it's not entirely. So let's say what is hidden. So right. So you consider the unit tangent bundle of the surface, and so since you have a representation, you have a flat bundle over this unitangent bundle. And because of the existence of this projector, so the splitting in that context of this subbundle of as a line plus item. Right. Now, so this is equipped now with a connection, flat connection lambda. So in other words, if you have the geodesic flow here, you can lift it to a flow over this by a parallel transport. So the geodesic flow plus the representation give you a bundle, and this bundle comes equipped with a lift of the geodesic flow by automorphism bundle.
And the line bundle is the lift of the geodesic flow generator.
No. They have nothing to do with it. But this line bundle, you see that you have a, okay, so this line bundle is parallel along pi t, meaning it's invariant by pi t. This one is also invariant by pi t. So this means that if you have a geodesic, which is an orbit of that, then you have above that a constant decomposition. Right? And this means that this decomposition, which is decomposition which is parallel along that. So that means that for this geodesic, you have a projector on this line parallel to this item plane. Okay, so this is the bundle. This is not, I mean, I'm not doing clever things about dynamics. It's just about bundles. And right, so where is the hidden property? The hidden property is that this bundle, I don't know which one does, but this one dominates this one in the sense that if you take the action on the bundle of on L tensor P star, this bundle is contracted, while the other one is contracted to other ones. That would be the analogous of the Anosov property. So that's a hidden part, and that's why you have this openness. Does kind of answer your question?
Yes.
Right. So now, set it to any geodesic, you have projectors. So here is you can find new functions, and there's a function. So there's length function which are interesting, but I don't want to talk about them because it's too complicated to define. But what you can do is now imagine you have a configuration of geodesics, G1, Gn, and you can take the trace of the product of this project. So that's good, but that's not good enough for a purpose. So now you may want to have it because I mean G1, Gn, it's not related to the group itself. The surface group is. So what you want to do now is you want to average that. So meaning if you have a gamma invariant measure on the product of all the space of geodesics, then you may want to consider this function, which is you just average this function over with respect to this measure when you take the quotient on that divided Gn divided by gamma. Okay, so let's explain again this construction. The first thing is that if you have n geodesic, you can consider the configuration of n geodesic. You can consider the this function, right? Which is just a trace of the product of the projectors.
And N is the same as SLN.
Oh no. Oh, cruel. Yeah, that's right. Cruel is the term, right? Yeah, I think that's why we usually stick in the field to SLDR, right? Okay, so and then you want to take the average. So let's give some example of functions that actually you know. So if you take two geodesic in the case of SL2R, so what is the trace of the product of the two projector? Is just something that is well known in the projective geometry, just the cross ratio of the input. So for hyperbolic geometry, in hyperbolic geometry, you take a representation, so your boundary at infinity is identified with RP1. So 4 points have a natural invariant, which is called the cross ratio. And this particular function is the cross ratio of the inputs. Right, but you can do that also in SL3R. So now if you take three geodesic exactly in this configuration, which is standard triangles. So what is this correlation function associated to these three geodesic? It's just what is called the Goncharov triple ratio. And I could give a definition, but this definition will just amount to say that's the product of the trace of projectors. Right. Okay, so now our main result with Martin Bridgeman is to say that you could compute the Poisson bracket of two of this average correlation function as itself an average correlation function. So let's say the first mu is related to configuration of n geodesic, and this is related to configuration of m geodesic. And what you do is that there exists a combinatorial Poisson bracket on the space of this configuration of geodesics. So given two configurations of geodesic, I can obtain another configuration of geodesic. And then the Poisson bracket is just the average for this object. Right. So there are still two corollaries. So the first one is essentially to say that this is what we started from. So it started from, for those who know a little bit of Teichmüller theory, the formulas by Wolpert, computing the bracket of two length functions. And then he has this formula that computes, it's called the Wolpert science formula, which computes the second bracket of that. You take three length function and take the three brackets, three possible brackets. So so somehow all this formula can be obtained through this procedure. And through this procedure, you have to use some classical dynamic facts about the homological equations. So the other corollary was really a motivation. It's about length function. So in this study of Anosov representation, so Anosov representation correspond to dynamical objects. They correspond to flows, and they have lots of length functions. We generalize the length functions for in hyperbolic geometry, and they also have a nice formula like that. But since they are a little bit more difficult to define, so but the question is whether these length functions are convex. So that's what we proved for some concept which is called positive representation. Okay, but let's not go there. Let's try to explain a little bit what is this Poisson bracket on configuration of geodesics. So I'm going to start with a very simple thing, very simple to state. So which is something I call the swapping bracket. So you start with the space of pair of the space of geodesic, which is the space of pair of points on the surface. Okay. And to avoid a cumbersome notation, I just denote a pair of point x, big X, little x by just this. This is just a short. So now you want to define. So you take the polynomial bracket you take, I'm sorry, you take this the polynomial algebra generated by this set. So the set of formal expression like I don't know. Sum of I don't know x y plus. So that's an example of an element in this a polynomial in this. This. So I want to define a Poisson bracket for that. So again, I just needed to define it for generators. So what do I do is that I define what is the bracket of x and xy just by this formula. So I take the intersection of these two geodesics, and I will explain why this intersection is +1, -1, 0, but it also can be -1 and 1.5. And then I just take the product, instead of taking the product of x and y, I just swap the extremities. Okay? I just swap here y with x. Okay. So what is this intersection? So let's so the first three cases you know about, of course, but you have to add also this kind of degenerate case whenever you have a pair of points with a common endpoint. And you have and this the convention is that this has to be 1/2 and the other has to be -1. And then since when you perform that, you may end up with, even if you don't start with something with common endpoints, you may end up with common endpoints. So you have the relation that xx is equal to 0. So whenever you see a formula where you have xx, big X, then you erase it. Okay? So that's the definition of your bracket. And right, so the kind of surprising thing that this is this very simple object is a Poisson algebra. So, and the only thing you have to check is essentially the Jacobi identity. So it doesn't seem so difficult to check, right? But we're talking about 6 points on the circle. So the first thing I try to do is, okay, let's draw all possible configuration of 6 points on the circle, right? But it turned out it's much bigger than I imagined. So if you are very stupid, maybe 200 something. So then I said, okay, so because my first thing is that, you know, this is a very simple object. So if you come up with a very simple object, so either it is known. So I checked with the various people around me, and they didn't know about it, or it's false. So I assume that it was false, right? So I picked some random examples. This did not work. So I said, let's do a computer program. So the first example I had was this is not a Poisson algebra. Does not satisfy Jacobi identity. So this configuration is not correct. Because I checked the configuration was correct. So I said, okay, there is a bug in my program. Let's write another one. So I wrote another one, and then what did the program said? Oh, this is a Lie algebra. But then when I looked at the program, I saw that I mean all this product was 0. So obviously it was not good enough. So in the end, I wrote like 6 or 7 iterations of the program, and in the end, it was only statistically true that it was a Poisson algebra because more than half my program said it was. So, so anyway, I went back to the blackboard and found it, which is not it's not too easy. Right. So so now I need to move from this swapping algebra to my configuration of geodesics. So I want to define, so remember that my goal is to define what is the bracket of two configuration of geodesics. Right, because I need to go back to this, I want to prove this formula, I need to have this, I need to have it to explain at least what is this, right? Right, so the first thing you do is that you actually replace you're a polygon, but why we call a gross polygon, which is so your configuration, you have a configuration of geodesic, which is G1, Gn. Okay. So what you do is you take the G1, Gn is exactly element of your generator of the swapping algebra. So then you take the fraction, formal fraction of these two objects, formal fraction here, and then you can sort of try developing using your Leibniz. Okay. So now let's explain what is this, what are these new edges that we call a ghost edges. So let's start with a configuration of geodesic, which is just this, let's say it's just 3 geodesics. Right. So now first thing is I want to turn that into a polygon. So this is the order geodesics, what's important they are ordered. So what you do is that you just add. So you have okay, G1, which is here.
Why do you want a polygon?
Because that's a title. So, but yeah, no.
Sort of knew that's going to make this work.
No. No, I mean, we really came out of the formula, right? So it turned out that to interpret this bracket, so just in the end, we didn't discover there's some relation with the swapping algebra. But before that, we did that just for this. So it's quite important to add extra edges to add this fraction. Right? So what you do is just you add the edges that connected this. Sorry, to connect this point to this. I mean, anyway, you see what it is, right? So you connect this to turn that into a polygon, and then you have to orient the edges. And then to orient the edges, you will remember that you're afraid of ghosts, so you go the other way around. Okay? That's all it is. So you have this ghost polygon, and you add this, which is adding these edges. And it turned out that now the Poisson bracket of these two things just formally is itself of the same type. Okay. So it looks like a complicated combinatorial structure. It actually is not that simple to manipulate, but with this kind of thing, it's not too difficult to obtain stuff like, so maybe I should write it here. So, right, so imagine that you have a H on G1. So for instance, if you want to understand what is this convexity of a length function, you just have to understand what is the bracket of G1, G0 on H. So let's say this. And well, you can do it just by computation. Okay, so I guess I finished 5 minutes earlier. So so the general result is again this this fact that you have a given correlation function, average correlation function. You can compute their brackets. This is helpful to compute stuff like to take iterate brackets of function of that. So why are you interested in iterate brackets? For example, a function. And if you want to go to this kind of object, so this is if the function is positive, it's the same thing as saying that if you take an orbit of the Hamiltonian of F, take G restricted to that, so G is convex. So to know stuff about second derivative of brackets is useful to understand convexity properties. So I think I should stop here.
Are these the only correlation function? Because don't you have like an algebraic, real algebraic variety?
Okay, so
Usually it's the traces of finitely many elements.
yeah, but well, I think that the result that for most groups, so there's some exceptional case, any algebraic function is in the polynomial generated by just characters.
Right.
So there's no, in some way, there's no other polynomial or no other algebraic function. But these are not algebraic.
Right.
Yeah.
Right. Okay.
Yeah, they're analytic though, but they are not, and they are just defined under some open set.
Yes. And these are the ones that come up when you want to do convexity.
It's the one that it's, and you know, you start doing, I mean, if you start to understand what is the bracket of two length function, then the first, the formula of Voltaire tell you that's related to the cross ratio. I mean, it's related to the angles, but which you can interpret as the cross ratio of the 4 points, right? So that's a generalization of that as for length functions. Okay.
So these correlation functions, I guess you said they're only defined for Anosov, so I guess they sort of belong as you.
Well, the point that you can't really define them because you don't have projectors. So I don't know.
The question is like, if Anosov is not the entire component, as you leave the boundary, what happens?
I think maybe in some case it converges because they are, you just need the fact that, right, for instance, if you're going to put in the quasi-Fuchsian case, so in some cases, so let's say you have the limit Cannon-Thurston map, so you could take 4 points so that they have 4 distinct images by the Cannon-Thurston map. So then you would define a correlation function for that, right? I mean, this is about real, but complexes work the same. So in that context, this is not going to blow up, right? But for other type of points, especially those points which are going to be collapsed by the Cannon-Thurston, which is related to the ending elimination, they are going to on the opposite to go to 0 or infinity. Does this answer your question? So it's the behavior is
I guess, yeah.
Well, yeah.
If you have something that's in the boundary of the space of Anosov, is there always going to be one of these?
Oh, one of those. Maybe this I don't know. Sorry.
But if you have those formats, it's like ratios.
Right, but again, there is this example of the quasi-Fuchsian going to the surface group that's fibers of the fiber of the vibration, right? So suppose this surface group, you still have cross-ratios for certain points in the boundary at infinity. So this means that your correlation functions are going to converge. But for some other case, they are going to blow up on the opposite. Exactly for those points which are collapsed by which are the endpoints of the ending lamination. So the situation is that's very interesting, but it's not yes or no. It's going to give you some information the way that some guys collapse and why some guys do not collapse. And then I'm just talking about SL2. Then when you go to SL3, the higher correlation, I should have said maybe that in the case of SL2, all these correlation functions, when there are more than 3 points, pre-geodesic is always 1.
Maybe you said it, but I missed it. So it's the Goldman bracket, a specialization of the bracket.
I didn't say it. The answer is yes or no. So So the yes part is, so for a curve, what you're looking is at the trace for the Goldman bracket. And in that context, you are looking at the length. So the length is what's the trace of gamma to the n. You take the log and take 1 over n of that. So there is some relation, but it's not direct. On the paper that relates swapping bracket to the Goldman bracket. So you have to take a sequence of covers of your surface, nice sequence of covers of your surface, so that this might make sense. Okay, I don't know if this is the answer, but it's not, the relation is not obvious. There is some relation, but it's really not obvious.
Can you extend this bracket to like the space of pairing with geodesic laminations?
Yeah, because this is, you take the average. So if you take the
Right.
average, it means that you take the average of a geodesic, it's just the current. So
Right,
So
so
you can-
that's useful for, that seems like more canonical.
right, so that's the way where it's
Oh, you're already doing that, man.
yeah, I'm already
Yes.
doing that, but this is the part which I don't talk about, which is the case of defining length functions for a curve. But we do have formula of the same type. We take brackets of length function defined as to a curve, and bracket of length function with the correlation. This is much easier to define.
Actually, I have a question, probably related, right, but, so I think you need the measure on the space of geodesics to be done by the.
Yes, I'm sorry. Yes, the measure has to be gamma invariant, and of course there is some certainty, which I of course didn't talk about, which is you better have that this function which is here is finite, right?
Yeah.
Because your averaging of g of j of mod gamma is by far not compact. So of course you want to have your Poisson a measure which is compactly supported works. But then for some reason you need to have, so essentially it works for those measure for which this is defined. So you have a notion of what is.
But my question was, so when you take GM cross GM, should it have been gamma cross gamma?
No, it's not gamma comes gamma, it's a diagonal gamma.
So it's not going to be an infinite measure space.
The space is not compact, but it turned out that in this form, oh, right, in this formula, yeah, this is very perturbing. But maybe I should write this. Yes, it is very perturbing, but it makes sense. Sorry, maybe I'm not.
Yeah, but before you did the quotient by gamma, the measure in GM is infinite.
Yes.
GM is infinite.
Yes.
So, but if you're taking only quotient by one compute, it seems like you should put something.
Right, but if you take the
Maybe it's not commuting after a while.
right, you may obtain something with infinite volume, but this guy is going to be integrable with respect to this infinite measure. So it's not a measure which is finite on this space. That's for sure. It's a measure for which this integral of this correlation function is finite. It was a nightmare to write, but it seems to be true.
A related question about the identity. The Jacobi identity.
Yes, the one for the swapping thing, or
Is it possible to put a kind of embedding disk on a surface, some copies of the disk? So deducing it from gold.
I'm buying any good proof because the proof I have is really, 3 pages. So I'm buying any good proof.